When we're computing the determinant of n by n matrices, it's a general process that actually works for 2 by 2 and 3 by 3, but it tends to be overkill for those. So it's nice to rely or go back to the special cases for those and use those, little diagonal elements for 2 by 2 and 3 by 3. When you get to 4 by 4 and bigger, there is none of this idea of a diagonal attaching things on the outside. There's just nothing there. In fact, we have to resort to something called the Laplace expansion formula, or it's also called the cofactor expansion approach. Now we're going to go through some of the underlying ideas here first, and then we're going to see it in context of an application. So don't get overwhelmed with what's going on the screen right now. Just wait until we see an example. I think it'll make more sense in that context. So the cofactor expansion requires two building blocks: a checkerboard pattern of signs. Whatever matrix size you're working with, 2 by 2, 3 by 3, 4 by 4, 5 by 5, whatever, imagine a plus sign in the top left corner, and then every other location in your matrix is associated with a minus or a plus or a minus in alternating sign as you move right or down. Now, if you remember back to the 2 by 2 and 3 by 3, remember there was this plus and minus kind of structure. This is how this plays out in the larger 4 by 4 and larger matrices. We're going to need that as a building block. In addition to that, we're going to have this new idea that when we pick any element, Aij, so row I, column j, we can make a smaller submatrix by crossing out that row and that column. So for example, if we are looking at the location, let's go A23, that's this cell, we are going to build a submatrix that is everything not with that column and not with that row. So that would turn into a 3 by 3 matrix that is here 1, 5, 6. We don't do the second row at all. We get 0, 0, 0, and then 2, 3, 1. So this is a tool we're going to need. We'll explain how it fits in a moment to the determinant calculation. Let's do another cell down here. Let's imagine for A41, so this one here. We would cancel out that row, cancel out that column, and we get a submatrix that's one dimension smaller of 5, 1, negative 6, 0, 3, 7, and 0, negative 2, 0. So for now, all we need to know is if we pick a cell, we can build this submatrix thing, and we just need to see how that fits into the determinant calculation, which we will address right now. How do we get a determinant using these building blocks, the checkerboard and these submatrices? Pick any row or column, and this is a single row or column. You don't have to do multiple passes. This is just one row or one column. In that row, you're going to have, in a 4 by 4 matrix, so you'd have 4 elements in that row or column. What you're going to do is compute the checkerboard sign, so plus or minus, plus or minus. You're going to take that and multiply it by what was in that element, and then you're going to multiply that by the determinant of the submatrix for that cell. At the end, then, you're going to take the sum of all these signs times this times the determinant. Now, for those, again, who have seen computing before, this can feel recursive because we're calculating a determinant, and inside the determinant calculation is the determinant of a slightly smaller matrix. Well, that would bring us back to the top, so say we had a 10 by 10 matrix to start with, we would do this calculation, and that would require calculating determinants of 9 by 9 matrices. We'd calculate those with the determinant of 8 by 8 matrices until we got down to some size that we could actually manage. In fact, here's the full recursive algorithm laid out. If you get down to a 1 by 1 matrix, then the determinant is just the number in that one element of the matrix. For anything larger than that, here is the formula. We've got this sign here, which should look familiar after your 172 series work. We've got negative 1 to the I plus j, that's our checkerboard. We've got the element of the matrix itself, and we've got the determinant of this submatrix ij here is the submatrix for that matching ij value, and we can add either over j as the columns, so we can pick a row, this would be row I, and we just add up over the columns j, or we pick a row j, pick a column j, and we loop over the rows I and do the same thing. Again, this is a horrible amount of algebra on the page. Let's do one and see how this works out. All right, so pick a row or column. Just because this is our first time, we're going to pick row 1. So this row here. Now I'm going to be drawing on this several times and then re-erasing. So if you're using pen for your notes, just be aware of that. Don't get too enthusiastic or this is going to turn into a total disaster of things being scratched out and then unre-scratched, things like that. Let's call this matrix A, and our determinant of A is going to be made up of many different ingredients. First off, let's get the sign chart. So the sign chart that goes with this is a plus for the 1 here, a minus for the 5, a plus for the -1, and a minus for the 6. We could put the rest of the checkerboard on there, but they don't matter because we're only using that first row. So I'm going to have a plus sign, and actually I'm going to combine those together. I'll put the plus in red, and then the 1 for AIJ, so A11, times the determinant of, so that's our checkerboard sign, there's the value in the cell, and then the determinant of the submatrix. If 1 is our value here, we're crossing off, this is the part I'm going to erase shortly, so don't get too committed, plus the determinant of the submatrix 0, 3, 7, 0, -2, 0, 3, 4, 1. Okay, now we go to the next element in that row. So plus, now it's the minus sign from our chart, our 5 from the values, that's our A12, times the determinant of, here 5 is our number, so we're going to cross out that row and that column. So what's left is 4, 3, 7. Isn't this fun? 4, 3, 7. 0, -2, 0, 2, 4, and 1. All right. And plus, we just keep going through the whole row. So erase all this stuff again. We have our value, which is -1, times the sign plus. So it turns out we just keep that -1. Sign from the checkerboard, times the cell entry here, 1, 3, times the determinant of, scratch out that column, scratch out that row, and we get 407. So there's a lot of self-similarity going on here, but unfortunately it really doesn't help speed up the calculations. And finally 2, 3, 1. And then we get a negative, sorry, I'll erase those guys. Then we have the 6 with a negative sign, so negative from the sign chart, the 6 from the A14, and thankfully we're almost done. The submatrix, if we are looking at that cell, is this lower left-hand corner, which has 4, 0, 3, 0, 0, -2, and 2, 3, 4. And this is why we invented computers. All right, what we're going to do is find these 3x3 determinants using what we know about 3x3 calculations. We're going to do that on the next page, and we're going to come back and fill in those values here. I think it'll be a little bit easier to work with. Just to give these names, let's call this matrix B, C, D, and actually, let's take one shortcut. Let's get one shortcut right now. If we have zeros in one whole row, then you can imagine the diagonal counting every time we do a product along a diagonal. Doesn't matter what the diagonal is. This equals 0. Thank goodness. Here we're going to have to be careful because not the whole row is zeros, but here, guaranteed, if we expand this out as a 3x3, we're going to get a determinant of 0. So it means we only need to analyze 3 of the matrices here and get their determinants. All right, so you might want to pause the video. What I'm going to do is copy these over to the next page as our building blocks. I won't bore you with showing all that. You can copy at your own pace, but we're going to have these on the next page to start, and then we're going to calculate those determinants. All right, so the determinant of the B matrix is this matrix here, and again, we're just tacking on the copy of the first 2 columns. That's our new technique for 3x3s. And trust me, it's faster than trying to do the recursive approach. And we're just going to boil that down straight to the calculations because a lot of this is 0, thank goodness. So again, because this is new, I'll draw them out in detail. These 3 diagonal lines down and right, we're going to get a 0, a 0, and a 0. So big bracket, 0 plus 0 plus 0. And then we subtract what we get for the other diagonals, the up and right diagonals. So most of those are going to be 0, but we're going to get something interesting here. 3 times 2 is 6, times 7 is 42, and there is a negative there. So negative 42 and 0 and 0. all of that equals positive 42. All right, recycle, reuse, whatever. Copy this down here, 4, 3, repeat ad nauseum, I think is actually what I was thinking there. 2, 4, perfect. So I won't belabor the lines here. It'll be 4 minus 2 times 1, that's minus 8. And then 3 times 0, 0. And then 7 times 0, that's 0. Plus 0 plus 0. Minus the upright diagonals. 4 times 8 is 28, and there's a negative, so negative 28. 4 times 0, 4, that's 0. 1 times 0, that's 0. And you do not need to write the zeros. I'm doing it now just for thoroughness because this is new for many of you. So we're going to get plus 20. I like putting the sign on there just to be super explicit that we haven't messed something up. Same process. 0, 0, minus, no, minus 2, just the first two columns get copied, 2 and 3. And so this determinant of this matrix with this 3 by 3 strategy is, close brackets, 4 times 0 times 4, that's 0. 0 that's 3 zeros again, that's nice. We like zeros. Zeros are nice. And then the up and right, we get a 0. And we get 3 times 2 times 4, that's not 0. Minus 6 times 4 is negative 24, so we'll put that in. And then another 0, thank goodness. That equals positive 24. All right, 42, 20, 24, all positive. That's fantastic. We can then sub that into our determinant of the big matrix. We're going to have 1 times, we said 42, plus minus 5 times 20, plus 0, that all went away. And then we had minus 6 times 24. That's 42 minus 100 minus 120, 144 actually. And that is minus 244. Oh, that's minus 202. These guys are almost the same. They almost cancel, but we have a little 2 left over there. So if we were in a 4-dimensional space, this transform, which doesn't have huge numbers, would take a hypervolume in a 4-dimensional space and scale it by a factor of 202 and have some kind of mirror image thing happening to it. That is one way to think about this transformation. The other thing that we learn right now, though, is that this matrix has an inverse. As long as the determinant is not 0, doesn't matter what it is, as long as it's not 0, this matrix will have an inverse. That was a bit of an ordeal, but I think it's worth thinking about ways to make that less of an ordeal. Starting with the same matrix, if we take that first step of picking a row or column, what we can do is look around and think, well, which has a lot of zeros in it, quite frankly, because if we pick this row, say, which has 3 zeros in it, that's the best row or column I can imagine. So we're going to pick row 3. Then our calculation for the determinant of A, let's do this over here. Yeah, let's do it here. Determinant of A. So this is our A matrix, is going to be, well, what do we need? We need our sign chart. So plus, minus, plus, minus, plus, minus. We only care about this row, so we can, as long as we get from the top left corner plus into the numbers we need, we're good. And then remember, we are combining the value and the sign and the determinant of the submatrix. We're multiplying all those each time. So we're going to have a plus 0 for that times the determinant of some submatrix. But do we care what the submatrix is? No, we do not, because we're going to multiply it by 0 anyway. No matter what that determinant is, we're going to get 0 overall because of that multiplier. That's why if we pick a row with lots of zeros, this is going to go a lot faster. Plus minus, this time 0, times the determinant of some submatrix again, but wait, we don't care because we're multiplying by 0, because this second element in that row is 0. It's only when we get to the third element that we get something a little more exciting happening. We have a positive sign, but then we have a minus 2, so I'm just going to, I'm sorry, this is plus. So we're going to have a negative 2 multiplier times the determinant of, and this time it matters. So I'm going to identify the cell that we're looking at, the matrix element we're looking at, cross off that column, cross off that row, and get the submatrix that goes with that. 1, 5, 6, 4, 0, 7, and 2, 3, 1. we're going to need the determinant of that 3 by 3. Then fortunately we can erase those and erase that. We get to the last cell and not a huge surprise. We have another 0 here times the determinant of stuff. And that again, because there's a 0 multiplier, is going to go away and equal 0 as well. So same matrix, but instead of having to find the 3 by 3 determinants for 3 or 4, it's 3 last time in our first strategy, now we just need to find this little determinant here. Let's call this matrix here E. Don't think we've used that letter before. The determinant of E is going to come from 1, 5, 6, 4, 0, 7, 2, 3, 1. And because it's 3 by 3, we won't go through this crazy Laplace or cofactor expansion. We're just going to use our diagonal trick where we multiply those and then subtract, multiplying these ones, which will give us the determinant of E equaling square bracket 0 plus 5 times 35 times 2 is 70 plus 24 times 3, 12 times 6. 12 times 6 is easier, 72, minus, in big square brackets, 0, 21, and 20. And that is equal to 142 minus 41. Oh, that's 101. Let's take that and put it up into here. So our determinant of A is equal to minus 2 times 101, which is, conveniently enough, exactly what we found in a much more laborious and painful process in the earlier approach. So the lesson here is, when you're forced to compute a matrix determinant by hand, if you can find a row or column that has zeros in it, by all means take advantage of that, because that'll help simplify some of the regressive work or recursive work that you have to do later on. There's nothing wrong with doing more work if you want to, but if you just want to save yourself some time and effort, if you can identify a row or column with lots of zeros in it, it will make your life a little bit easier. Finally, as we wrap up this week, let's make a quick comment on the things we've seen so far. So when we've been looking at determinants, we've seen that if we have some area and we transform that with some L or L sub A and get some new area, we scale the area, so closed regions, by the determinant of A and specifically absolute value, because the sign means something different. But it's enough to say, in most cases, to look at the scale of the change. So if our determinant of our matrix was 2, any area that we map or transform with this linear transformation is going to double. If it was a 10, the area would increase by a factor of 10, multiplied by 10. We also saw that if A is invertible, that is equivalent to a whole bunch of things, but our new ingredient here is that the determinant of A, think about areas, as long as I get a new area, I can presumably map it backwards. Where do things break down? If I squish the area until it collapses a bit, so the determinant cannot be 0. We also have the condition on sequences of matrices. So if I have 2 matrices and I multiply them, thinking about multiple transformations, the determinant of that, the net effect of that, is going to be the same on the scaling and mirror images, at least, as doing the determinant of each of the individual transformations first. So that's a lovely fact we have. Another fun thing we haven't actually talked about, but it's a nice corollary to this, because we know that A times A inverse equals the identity matrix. And if you look at the identity matrix, its determinant is always going to be 1 because it doesn't change anything. So if we talk about the determinant of A and the determinant of A inverse, well, it's going to equal the determinant of the identity matrix. So thinking scaling, this is going to equal 1. If we know the matrix A's determinant, what's the determinant of the inverse? We'll think about it as L inverse of A. If this doubles the area, we're going to have 1/2 the area when we do the inverse transform. And we see that here through this logic, that the determinant of, let's get a little more space here, the determinant of any inverse is going to be 1 over the determinant of the original matrix. We're going to see that come back a little bit next week. So if I have something that doubles the area and I inverse it, then I'm going to have a determinant of 1/2. If I have 10 times in a forward transform, the inverse is going to have a determinant of 1/10. And finally, just a quick little summation so we can see it all on one page. If we have the ABCD 2x2 case for matrices, we simply do the cross multiplying where the determinant of that matrix is A times D minus B times C. Make my D a little more pronounced there. 3x3 is a little more complicated. We won't show that explicitly here, but it's the copy the two columns, bring them over, and then multiply through, and then multiply through on the other diagonals. And the n by n, we won't even try to draw in abstract. This is the combination of the checkerboard and the submatrices. And those give us both some insight into what the determinant means and why we would want to compute it in various scenarios. Tells us information about what the transform does, and also gives us early clues as to whether a particular transform is invertible or not.